Now if you take a normal pencil and plug it into several power supplies, you can get up to about 48 volts. And when you kind of turn the power on, what you find is it starts to glow. And as the kind of graphite centre of the pencil gets hotter and hotter, it gives out a lovely red light and it kind of turns orange and eventually white. And you might have noticed this before, that basically the colour of something tells you a bit about the temperature. In fact, this is why people who are welding, where you have a really high temperature at the end and there's some ultraviolet light given out, this is why they wear masks to protect their eyes from the ultraviolet radiation. And basically, there's a guy called Wilhelm Wien, and what he found in about 1893 was the link between the temperature of an object and the wavelength of light that was being emitted. And what we can do is we can draw a curve of the different intensities of light which is given off. So on the y-axis I'm going to have my relative intensity. And then on the x-axis what I'm going to have here is the wavelength, going from short to long wavelength. And what we find is that if you have an object at a certain kind of temperature, what we get is a curve that looks a bit like this. And what we find is that there's a certain point, effectively most of the radiation is given off at this certain maximum wavelength. And what we find is the area underneath this curve is equal to the total intensity of all the light emitted. But what we find is that for every different temperature, there's a certain maximum wavelength of light which is given off. Now, every object which is above 0 Kelvin emits EM radiation. And what we might find is if you have something which is maybe at a different temperature, we get a curve a bit like this. And perhaps we have something which is at an even cooler temperature, we get a curve that looks a bit like this. It's supposed to be kind of a smooth line down there. Now, effectively, what we find is that there's a link, and this is what Wien found, was there's a link between the maximum wavelength of light given off, which is lambda max, and the actual temperature of the object which is emitting radiation. And these curves here are the curves for what we call a black body. Now, a black body is something which is basically a perfect absorber of radiation, and it's also a perfect emitter. So these curves here represent what actually happens to starlight, and we can assume that a star is basically acting like a black body. It's a perfect emitter of radiation across all parts of the spectrum. And this leads on then to Wiens Displacement Law. Now, Wiens Displacement Law, and Wien is spelled W-I-E-N-S, and so it's his displacement law, basically states that the maximum wavelength of light given off is proportional to 1 over the temperature of the black body emitting that radiation. And we can also write this by rearranging this. We can say that lambda max multiplied by T is equal to a constant. And the constant in this case is Wien's constant, and it has a value of 2.90 times 10 to the minus 3 meter Kelvin. So this Wien's constant basically then allows you to work out, perhaps if you know the temperature of a body measured in kelvins, what the maximum wavelength of the emitted light is. And this is why when something gets hotter and hotter and hotter, the wavelength gets shorter and shorter, and it goes from like the red part of the spectrum towards the blue part of the spectrum and then into the ultraviolet. But you've got to remember that even things which are quite cool, they have a certain quite long wavelength. And this long wavelength then puts them into the ultraviolet part of the spectrum, into the infrared part of the spectrum. And this is how infrared cameras work. They can pick up things like yourself, like you've got a temperature of about 37 degrees, so about 300 Kelvin, but you're still emitting radiation with a certain wavelength. So I hope that helps. And my next couple of videos talk a bit more about temperature and then how you can actually use this information to actually work out what's going on inside a star.